Welcome to my booth. My name is Hembo and I'm a first-year PhD student with Jarvis. In hopes for a cheaper, solution-processable alternative to silicon solar cells, organic photovoltaics have gained a lot of attention in recent decades. The highest recorded power conversion efficiency exceeded 18% using narrow bandgap non-fullerene materials. Unlike their inorganic metal counterparts, intramolecular forces play a dominant role, and the excitons formed in organic solids or polymers are much more tightly bound. This meant that charges can only be separated when they're at the interface of materials of different work functions. However, only about 10 nanometers of material closest to the interface can contribute to the photocurrent generation. Different designs have come up to promote more current generation, and this includes bulk heterojunction cells, where we blend the two materials in order to shorten the path of exciton diffusion. The materials should be chosen so that their valence and conduction bands, or in our case, the highest occupied and lowest unoccupied molecular orbitals energy levels, are lined up to promote exciton dissociation. The resulting charge states should then be free to diffuse towards the collecting electrodes. How well the charges separate can be described with OPV's fill factor, but the underlying influence on the charge separation remains unclear. Causes like recombination or poor charge mobility can play a significant role on the fill factor. To better understand the origin of charge separation, we need to better quantify the charge transfer states. Through-space polymers are designed to have donor molecules covalently bonded to acceptor molecules. By doing so, we can control the number of charge transfer states that are being generated. This is unlike bulk heterojunction cells, where their interfaces are formed through phase separation, which is based on the system's desire to minimize free energy. Preliminary experiments and modeling have been conducted on these materials. Calculated oscillator strengths for the transitions from the ground state to the excited states are shown. Using tight binding molecular dynamics, I calculated the ground state coordinates of at least 20 conformations sampled from a thermal bath of 300 Kelvin. This gave a more accurate representation of absorption data than that from one ground state geometry. Theodore program package was then used to analyze the types of charge transfers based on quantitative properties like the exciton size, charge transfer number with respective to the donor acceptor fragments, and exciton correlation. I also measured steady state and transient photoluminescence of solid-state films to compare to our time-dependent electronic structure calculations. We're currently developing methods to characterize the true nature of the excited states of larger systems and to describe the excited state dynamics in a tractable manner. Our overarching goal is to design op conversion materials for photovoltaics.